All right, continuing on with example 4. Um, some of this is just going to be reviewed to you guys, so it's not going to take a lot of our time here to go through this. Then you can get working on finishing up your homework. I know that in the past problems I've said set it equal to x, but what I want you to understand is they're asking you to evaluate common logarithms. You're using a calculator. As you can see, these are all base 10 logarithms. So, log 34.5. I mean, it's not going to be hard for you guys to reach over with a machine, log 34.5, and see that it's approximately equal to 1.538. Okay, so we're just typing on a calculator. Nothing big about, log 0.43. Now, the only thing I would say or understand is, so 34.5 is between 10 and 100. Well, so this is 10 to the first, and this is 10 to the second, so it makes sense that the exponent on 34.5 has to be something between 1 and 2. So when I get to log 0.43, and I'm ending up with negative 0.367. Okay, now why is that negative? Because we know that 10 to the 0 power is equal to 1, and 0.43 is below 1, so that means that the exponent has to be below 0. Exponents can be below 0. Now, just as a reminder, what does a logarithm graph look like? All right, so every logarithm graph looks pretty much the same as we talked about before, right? They all look somewhat like this, and base 10 would be no different. And quite honestly, it wouldn't matter if it was a natural log or what base it was. They all look pretty much the same. And if there's been no scale changes or any kind of shifting going on, they all contain the 0.10. But the question I have for you is, what's the domain of the function? Well, hopefully all of you know that the domain would go from 0 to infinity. This question is asking you, what's going on out here at -3? And I hope in your mind you're saying, well, Mr. Staley, there's nothing out there. That's right. This has no value. There's no solution to this, okay? Because -3 is not even in the domain of a logarithm function. If you get a question like that on a test, it's supposed to be an easy answer, not a difficult one. Now, when we get to solving simple logarithmic equations, this goes back to what we talked about before, changing to its exponential form. So some of this is going to seem a little bit redundant, right? You got to look at it, say, find the base. Find the exponent. Well, in this case, the exponent is not the unknown quantity. It's a 3. The unknown quantity is the argument of the logarithm. Now, in order to do this, you must have a single log, okay? Just like the song says, all the single logs, all the single logs, all the single logs, all the single logs. You know what I'm going to say next, right? If you like it, then you better put a base on it. That's right, folks, the rest of the song. Anyway, so we get an x value of 1,000. So if it's a single logarithm, we can switch it to its exponential form. You'll never hear that song the same way again. 2 is the base, 5 is the exponent, x is the argument that it equals, and everybody knows that 2 to the 5th is 32. So, should have put an S on it. If I like it, then I should have put an S on it. All right, this is ridiculous. All of the same properties are true about base E logarithms, except for E is 2.718 approximately, not 10. I'm sorry for yawning. Don't hurt me. I know some of you hate it when I yawn while I'm taking notes. Let's see here. We'll set it equal to x. It is a single log, so we can change it to its exponential form. What is the base? Base to the exponent equals something. And then we'll fill in the boxes. Let's see here. The base, well, folks, the base is right down here. I know you can't see it. It's in like super microscopic print. It is an E. All right. The exponent, well, remember, logarithm, a single word synonym for logarithm is exponent, right? You have to understand those two things are the same. Okay, so x is the exponent, that's the logarithm, right? And then it equals the square root of e. Well, we rewrite this as e to a power, and then we know the answer to the question. X equals 1/2. All right, continuing on here, we set it equal to x, and then rewrite it into its other form. Something to the something equals something, just like we did the other day. You got to pay attention to the fact that the base is not written in there, but we don't need it written in there because it is base E. What you assume, what you need to understand is that e to the 5th is part of this equation, but it's not part of the base. Okay? So the next thing in my list, if I've identified the base, sorry, I should use a different color just to make sure. So I've identified the base. The exponent's sitting here on the other side, right? And it equals e to the 5th. Well, that makes it very easy. X equals 5. All right. Now, this is the one where we don't change it to its exponential form because it already is in exponential form. We change it to its log form. We want ln. Now, we already know what the base of an ln is. It's an e. So there's really only 2 boxes to fill in here because we already know that that's base e. A logarithm is an exponent, so we know that the exponent is natural log 4. That leaves only one thing left. That leaves the x go here. Well, so what does that mean about x? If the left side equals the right side and the bases of the logarithms are the same, then the arguments have to be equal as well. Okay, this is not any different than what we just talked about a few minutes ago. You type it on a calculator, okay? And, you know, e to the first is approximately 2.718. E to the second, e to the second is approximately 7.389. E to the third is approximately 20.086. So you know the answer to this question is going to be higher than 3. And if you type ln 23.5, you get 3.157. 3.157. So you know that's And that makes sense. This is obviously going to be a negative number because it's smaller than 1. Natural log 0.48, negative 0.734. Okay, and then of course this one, well, remember how we talked about every logarithm graph looks like this, and you're asking me for what's going on at negative 5 out there? Oh, solution. Right? The basic logarithm graph, like I said, for a natural log, all of this stuff that you've talked about before, domain, range, continuity, where's their vertical asymptote on the graph? It is an increasing function. There's no symmetry, so it's not an odd or even graph. It is definitely neither. Not bounded above or below. No extrema. So no maxes or mins. Definitely no horizontal asymptotes. Vertical asymptote we already described as the y-axis or x equals 0. Okay? Like I said, all of the log graphs have a similar shape, and you can see that they go through the point 1, 0. Domains and ranges are all going to be the same for each one of these. Asymptotes the same. Very little differences. Now, what happens when you start transforming these things? This is where we're talking fireproof form. What does fireproof form look like for these things? Okay, so every y gets substituted with y minus k over b, and every x, now this could be ln, this could be log, it doesn't really matter, but they're all going to look something like this. So you need to be able to look in here and say, oh, okay, so that is a left 2. There wasn't anything to do with letter A. When you look at letter G or C right here, you could divide on both sides by 3. Y over 3 equals log x. Well, that's telling me that there is a vertical stretch by 3. Kind of hard to draw those on a graph with logarithms, truthfully. Now, there's two things going on in letter B right there. Okay. In letter B, notice that inside we want it to say x minus h over a or something like that. And what's the coefficient of the x term? It's a 1. Okay, so they've done a little algebraic razzle-dazzle. Yeah, I know, there's a good term for you. How do I make that coefficient go from a negative 1 to a positive 1? Yeah, you multiply everything top and bottom by negative 1. So this becomes x minus 3 over negative 1. So we could rewrite this as h of x, or we could call it y. Y equals the natural log of x minus 3 over negative 1. Now, why would I want to write it that way? So that we could easily see that it has moved right 3. And because we multiplied the x's by negative 1, that is a reflection across the y-axis. Remember we talked about if you look at a graph, took a random point, and you multiplied either the x or the y, in this case the x, you can see which way it moved. Moved across the y-axis. And in this last one, letter D, They're just trying to, I mean, why write it on the other side? But you could y minus 1 equals log x. So there's your fireproof form. So you can see that there has been a movement up 1 unit. Now, what kind of changes to a logarithm function would change the asymptote? That's the question that's important. Any kind of left or right shift is going to change that vertical asymptote. So, if I would ask you for, let's say I would ask you for the picture on A. How to transform the, okay, so let's say I wanted to do A. We wanted to move it left 2. I would expect that you would have a basic looking picture moving left 2. Now, the truth of the matter is that if 1, 0 used to be the point on the old graph and you move it left 2, it becomes that point right there. So negative 1, 0. But anyway, so that's the particular, if you've gone to the left 2, so x equals negative 2 is now your vertical asymptote. Things like domain, negative 2 to infinity. I mean, the range isn't changing. It's still all reals. Now, on letter B is a little bit different, right? Because they're doing that. They're moving right 3 and they're doing a reflection. So, truth of the matter is you need to do the reflection first because it's part of the multiplication process. We all know that multiplication comes before addition. So, first you basically had this graph that you reflected over the y-axis for letter B, but then you shifted it over 3 units. So you have your vertical asymptote, and I don't know why that moved over like that, and vertical asymptote there at x equals 3. And so then your shift comes up and does something like this. So reflected first and then moved right 3. Example 9, you buy a used car for $3,000 whose long-term residual value is $2,000. The time and years that it takes for the value of the car to decrease to whatever V is in thousands of dollars is given by this function. Graph the function. Explain how the graph is related to the graph of that. Well, obviously it's been moved to the right 2 units. And so negative 4.5 natural log, and I'll use x minus 2. And so we get something when we graph it on the calculator. 2 units over, there's your vertical asymptote. Because of the negative multiplier, we are doing something like this, because it's a reflection across the x-axis. So first it got reflected, then it got shifted over 2 units to the right. So, why is it, why does it look like this? It says the long-term residual value is $2,000. That means it's going to stay, as time goes on, it's going to stay close to $2,000. Will it go closer to, will it go below that? Sure. But according to this, oh, I'm misreading this particular graph. So the time on this axis is actually, that's your time is here, value is here. Value is your, it's normally time is on the x-axis and value is on the y-axis. Okay, all right. So the value of the car is significantly above, or is, as time moves, am I reading this right? Hold on a second. It's kind of weird graph. I'm not really going to put one of these on a test or anything, but you're starting at a time of 0. So you've got a time value of 0, and then as time moves, gets higher and higher and higher, the value of the function gets closer and closer and closer to that a vertical asymptote. It's kind of a weird way to show this particular, because like I said, time is usually your horizontal value or horizontal measurement, and value or money is the vertical, and so that's why this looked a little weird to me when I first started out. I would be more interested in graphing it as an exponential decay function. That would make more sense to me than doing it something like this. I'm not going to get into this decibel example. So you can work on homework now that we're done with the notes.